Okay, folks. That was Monday, and we did user-defined functions, and I think we struggled. Is that correct? Okay, so this is the beauty of this class, that sometimes stuff will slip. So Zuri is completely ready. She's going to tell you all about graphics and visualization, but she's not going to tell you that until Monday. So what we're going to do today is I'm going to just go through good programming style really briefly and talk about expectations in the class, because you see this. Homework is due at the end of the week and everyone's freaking out about it. Yeah, this is Friday. Friday by the end of the day, essentially. And so now you've been really curious because obviously you've already started on the homework, and having started on the homework, you're like, well, what do you mean by good programming style? So we'll talk about good programming style and how you can get the most points out of that homework. And then we'll move all of this stuff to Monday, and therefore everything else will slide a little bit more. Is that okay? Okay, any questions? Is homework in week 3? Oh, doesn't it just say homework 1? There's a different file for homeworks. So there should be a folder called homework 0. And if it's not open yet, I apologize. You can also move, let's say you are working in week 3, you can move a file from week 1 to somewhere else. And I can show you how you can do that today if that's not already available. It's not open? Okay. For homework?
The folder I have is for
But I haven't assigned homework yet. Oh, okay. Okay. So there's like a hidden layer, and I'll show you in CoCalc. So by the end of today, I will assign you all an assignment called homework 0. And that's where you'll put those 3 problems.
Do you see the folder you create with that?
Yeah. I see everything, right? So everything that you're building, right? Even if you just have some scrap work, if you're like, hey, can you go check out, file test2 underscore, I don't know what I'm doing. I can go look at that as well. So let's just remember a couple things about this. When we are writing the names of any files that we're using, we're not doing exercise 2.2 in the name of the file. Why is that? Anything after a point is a file extension. It's telling the computer what kind of file it is, not that it's exercise 2.2. So generally speaking, I would encourage you to do things like saying what your name is or what the homework is. You can say homework 0. Don't say homework pound symbol 0. Just say homework 0. Or say, problems that are hard, number 1. Problems that are hard, number 2. You can call it whatever you want. Just avoid special characters. I'd say special characters, that is basically anything that's not a letter, right? Generally speaking, you can rename files. So it's not as though if you create the file, that'll be ruined forever. I just have to download the file, change the file name, and re-upload it. But you may find that CoCalc doesn't like it. Does that make sense? Okay. So let's go back to the syllabus here where it has, wait, actually, let's go to, yeah, this is fine. Let's go to homework. And here's where we were talking about the homework as a whole. And remember, this is the way that we are going to consider the problems, okay? Does your code contain an algorithm, regardless of whether or not it works, that will, in theory, solve the problem? Okay, that's where you're getting most of your points. So if you identified the right tools, good. And this can even be a conversation, right? Let's say you start off at the beginning of your homework and you say, I know that I'm going to need a for loop to go through the Z's, and then a for loop to go through the A's. And then I need to ask it a bunch of if statements to calculate what coefficient to use here. And then I would calculate the B for that, and I'd find the max. I'd say that is an algorithm, right? You start at one place and you get to the end. And if you coded it out, that's even better, right? That I would give you the full amount of this number 1. Now, if it runs, then you get number 2, right? But sometimes, only the first half of it runs, or it ran for the first 2 parts of your problem, but then you made a change in part 3 and it didn't run. And again, here, I would ask you to communicate with me, not just verbally, but also in your homework, write a comment. This was working until I made this change, and now it's freaking out, right? Because that's where I can draw my attention, be like, oh, I see what happened, okay? Similarly, let's say you do get to the end, and you ask yourself, does this give the correct answer? How do you know it's the correct answer? That's not so easy, right? And so this is something that we're going to build into our understanding of doing computational physics. So in the very first couple of homeworks, I'm going to encourage you not to think as much about the physics, okay? So Eduardo was talking about this example where we have to imagine what it would be like traveling near the speed of light, and the velocities change and the distances change, right? And I just wrote something arbitrary on the board here about how to do the velocity transformation. If you use that, you may have no intuition for what the right answer is, right? But what you could do is you could test it. So you could say, well, at v equals 0, I would expect something like this to happen. And at v equals c, I would expect something else like this to happen, right? That is a perfectly good way of testing your answers. We call that checking the bounds. And you sometimes do that when you're thinking about a function overall in physics, right? Regardless of whether or not you understand special relativity. Does that make sense? Another way of doing this is you say, okay, I want to produce a list of numbers, okay? And your list of numbers is going to be all of the binding energies, maximums of all the binding energies. Well, how would you check that to see if it might potentially be right if you don't have a textbook in front of you that has the right answer? Step 1, it gave me a list. If it gives you a single number, then you didn't do it right, right? So if I got a list, oh, good. All right. And I printed the list out, right? And then it asked me to find the maximum in that list. So I printed the list out and I looked by my eye and it did the right thing. It grabbed the right number, right? So what you can do is as you're moving through the code, check your work. So before you start writing off Catalan numbers from 1 to 1,000,000, check the first 4. If the first 4 are right, and you can reference that against something, then you can be really confident, or at least as confident as you're able to, that the next 30 or 35 will be correct. Does that make sense? I won't accept the answer of, well, it's just right because I know that it's 7, right? That's not an answer. I want to see internal testing. So debugging is a lot of coding, and it's the worst part of coding. But as we get better and better at coding, it's going to become more of our time because we'll write the code really quickly and then it won't work. Okay. And so you'll have to figure out, well, why did it break and what tests can I do to find out where it's breaking? Right. Okay. And then finally, is it written using good programming practices with extensive comments? And so now is when we're going to talk about section 2.7. So any questions before we transition? Okay. Come on now. All right. So here's 2.7. Oh boy. Oh boy. That's not what I want. Okay. Good programming style. So generally speaking, good programming style is simply an indication of basically good communication, in my opinion. So part of this class, believe it or not, has to do with our ability to communicate to one another. I know you think physics is like, well, you can just be quiet in your room and not talk to anyone. But in fact, you will need to get this thing called a job at the end of this. And at a job, you will have people who you work for and with. And being able to communicate effectively to the people you work with will make your work better. And being able to communicate to the people you work for will make you more money. So if you can demonstrate how great you are, raises. If you can demonstrate why your code works to your colleagues, then they can use your tools, right? Okay, so that's why we're thinking about these presentations at the front are not simply, okay, he's lazy, he doesn't want to talk. I love hearing myself talk. I just sit at home and I just talk to myself. Okay, that's not the point. The point is to practice communicating in front of others, right? So there's lower risk here, lower stakes. And as you see later on, when you do your final project, you're kind of building up to that final presentation. Does that make sense? Okay. So I encourage you also to be asking your colleagues questions, right? Think of everyone in this room, not just as other students, but as peers, people who you potentially might work with, right? Maybe your network for finding jobs. Okay. All right. So, I like to say some things about good programming style. It's communication, right? So for example, we have been using like letters like Z and A. You can do that. There's nothing illegal about doing that. But you may find it's more instructive to name your variables. So like atomic A or atomic Z, right? That way you're not missing out on what it is. And reserving letters like I to be something that is just counting, or K is something that's just counting. As opposed to when you're doing velocities later, you might do vel underscore X, so that you know that's the velocity in the X direction, right? And having a little bit more thought, as opposed to just saying Vx or X, right? That might help you a little bit more. XPOS would be exposition, right? X ACC, X acceleration. That's perfectly good. You don't have to write out the whole word, but you're welcome to too. Okay. Okay, wait, what happened there? That page has disappeared. Good programming style. Don't leave things blank. Oh wow, yeah. Okay. Does anyone have the book on them? Yeah? Can I have it? Okay, do you know what the first one is? Yeah. Wait, is this from the sample chapter?
Yeah.
Is the sample chapter blank? Okay, what is the first one? Okay, so I've been already hammering this one home, right? What kind of comments are you including? So remember the requirements here, the things that I really want, start at the very beginning. Who are you? What problem is it, right? At the beginning of your homework, you should identify your name, okay? You should identify what week homework it is and what problem you're working on. Next.
Use the meaningful variable names.
Meaningful variable names. Oh, good. I already just said that, right? Something that will help you and help me understand what is being said.
The right type of variables.
Ah, so this one's a little tricky, right? So now you're going to have to pay attention. Should I have used the list here? Should I have used an array here? And sometimes, you know, I said that coding is artistic, right? There's multiple ways to do it. I'm not going to really come down on you hard and say like, oh, you should have used a for loop here instead of a list that you filled. That's fine to do them either ways. But you will notice as your codes begin to get longer, you may find that too many moving parts will confuse you. So if there is a more clever way to do it, I'll just comment that or tell you, and I'll point it out in the code and I'll say, look, I think right here, you can combine these 3 lines into this one line. And you'd be like, oh, whoa, right? Okay, next one.
Import function first.
Right. So we're always going to start with our block at the very top. And the nice thing about that block that doesn't have any user-defined functions in it, it doesn't have any code in it other than the names that you have, the problems that you're going to be working on, your comments, and then import numpy as np and import time as o or whatever, right? You're going to have a whole bunch of libraries that you want to use. And you'll notice when you start looking at code that I present, like actually code for my research, I just copy and paste the same bunch of pieces. I say, I always know that I need this, right? I know that I need matplotlib in order to make cool pictures. I don't want to remember all of the different other ones I need. I just copy and paste it to the beginning of every piece of code. Because if you have the directories loaded, but you don't use them, who cares, right? Okay, next.
Give your constants names.
Give your constants names, good. So in some cases, this isn't as necessary, so when we're doing the binding energy one, A1, A2, A3, and A4, that's fine because I don't have a physical interpretation of what that is. But if we are doing a problem where we're measuring the rate of foxes being born and rabbits being born, and then how quickly the rabbits are getting killed by the foxes, which is a problem that we will do when we get to differentials, you'll notice there are constants there that make sense. So you could do birth rate for foxes, and you could have a nice little comment, and you could say fox underscore BR, birth rate, right? And that would be enough information that is some constant that is going to be multiplied by something else, right? Okay. You'll notice that it gets a little cumbersome. And I don't know how good spellers you are, how well spell, whatever. You get it. I'm a bad speller, and I'll tell everyone this right away. So when I write code, this is one of my biggest downfalls, is sometimes I'm writing the word target and the variable name is targets, right? That's like, or target, right? And then I just miss the R at all, right? Okay. All right, let's go to the next one here. Employ user-defined functions where appropriate. So this one is a double-edged sword. So we just learned about user-defined functions, and I always see this happen. So I'm just going to tell you this now. It's perfectly okay. Your first instinct will be to turn everything in your code into a user-defined function. Okay? That's not right. But also, it's not right to never use them where it's necessary. So if there's a task that requires some input, stuff happens, and then something comes out, that is a totally valid place for a user-defined function. And you will kind of get this sense as you go through coding. You'll learn when they're usable and when they're not. When it's all encapsulated into one thing and, it's like a magic box, user-defined function. If stuff happens and you update in here and you might need some of it later, not user-defined function, right? Okay. This is one that kind of goes to point 3 of the homework rubric that I was talking about, where how do you know if it's right? How do you know when it broke? This is really going to help you do that. That is to print out partial results and updates throughout your program. So it doesn't cost very much to type in the letters print blank, right? And sometimes when you're having an issue, let's say the code's not running or you get an error, one of the things you can do at home, and I'm not saying you shouldn't contact me, but before you contact me, you can ask yourself, well, how far along did the process get? Let's say I wanted to update Z's and A's and find out the binding energies, right? Let's say I wanted to do all that. Did it run even once? Right? So you could say, well, print A. And if A is still 1, then it didn't run. But if A is 100, then it probably did run, right? So you can print out partial results the whole way through. Okay. This one is more for me than anyone else. I'm going to really try to come down on you a little bit hard at the beginning of the semester and say, like, put more spaces, right? Don't have line after line after line after line right on top of each other. Show some structure. Put a space in between. If there's this section does something, put a space between that and the next thing that does something different. Even if you have for loops, right? If you have a for loop like this and a for loop underneath it, and this one is inside of this one, so it slides over, it's indented, now separate them. So that you could say, okay, this one does the first thing, and maybe you even write a little comment. This is a different loop, right? You can have that separated. It'll just look pretty. You'll feel better. Okay. Questions? This one is impossible to know right ahead. It says, don't make your programs unnecessarily complicated. You won't have an instinctual response. You'd be like, are you kidding me? Everything is unnecessarily complicated. Why can't we do this on paper, right? I can look up prime numbers online. What are you doing, Prismani? No. So the idea here is as you get to know it a little bit better, you'll realize, oh, wait a second. I didn't have to make, a bunch of lists that then I emptied and refilled and emptied and refilled and emptied and refilled. What you want to think about is, okay, what do I actually need here? Okay, I just need A and I need Z, but I don't need to remember them. So I can forget them as soon as they existed, right? And that will help you sort of get rid of the clutter. At the very beginning, you won't notice a difference in your coding. When you start doing, say, a simulation of, an electron and a proton and what their electric fields are, you'll notice it's going to take a little bit faster. It's take a little bit longer. So the more that you're copying and pasting large pieces of data in your code, the harder it's going to be. That make sense? We'll come back to that one. I'll try and just like poke you on it. And that's it. That's section 2.7. Okay. Any questions? Okay. So as promised, oh God, where'd it go? Bleh. Okay. So as promised, we are doing what was this one? Yeah. We are going to finish up 212 today. I think folks made a valiant effort. Some folks, were underwater and none of their computers were working. That's okay. So we're going to try it again. And I'm going to go ahead and I'm going to put it up here. So why don't, while I'm getting it up, why don't you get into your groups that you're in before and maybe pull up a piece of code, and then we'll talk about how we set up the algorithm. Who are you working with? You were working with someone last time, right? Okay. You must have been in a group of 3, right? But why don't you work with Brandon right now? Because I think we have more people today. 2, 4, 6, 8, 10. Yeah, I think we only had 9 last time, maybe. Yeah. I don't really know how many people are in this class. I think it's 11. I think Jadden's not here. Okay, folks. So generally speaking, how do we do problems? We write them down on math paper and then we paper it out in math. Okay. So generally speaking, I'm going to do a little bit of a demonstration as to how we would attack a problem like this. And then you can sort of try it on your own. Okay. And you'll notice that I'm not going to be doing it on the computer. So I would strongly suggest, if you are the navigator, you can have the textbook up too, but you're not sitting there typing while you're doing it. You should have some sort of game plan. I told you that the first part of the homework is, does the algorithm solve the problem? So the first part of problem solving is finding an algorithm to address the issue. Okay? So let's start here with our example of primes. So we had some piece of code, and that example about primes, oh no, do we have any of the good stuff? I'll just put crime. Oh, this is cold. All right. Okay. So the goal, primes. Okay. So that's more than one number, and I know that because of the S. So that tells me I need what? A list. Why do I know it's a list and not an array? We don't know how many we need yet. It's more than 2. I know the first 2, 2 and 3, but it might be 100. So I can't say that until I know. Okay. So the goal is some primes list. And I know that I'm gonna need a user-defined function because this is in the user-defined function area. So I'll need some user def, right? And I know it's gonna take some stuff in and it's gonna spit some stuff out. Okay. Does that make sense? Okay. So let's look here. It says it checks to see the example in the program in example 2.8 is not efficient. It checks each number to see if it's divisible by any number less than that. We can develop a much faster program for finding prime numbers by making use of the following observations. And then it states 3 observations, and I told you to do them each at a time, right? You may or may not have taken that as do not read anything. I hope you don't do that. Because if you read the bottom paragraph, it tells you what to do. So it says specifically, write a Python program that finds all the primes up to 10,000. Okay, so now I know that I'm going to be doing something up into a point, right? So if I have something that starts at the beginning and goes to 10,000, what kind of thing is that? Range, and ranges are inside of for loops. Yeah, so that's the right idea, right? You hear it now when you hear go up to, right? So if you know how long it's going to be, that's the right way to do it, right? So you say, okay, 4 has got to be in there somewhere. And you're probably going to start at the bottom. So let's say like 2 to 1,000. What is it? 10,000. 10,000. Okay, so there's a for loop. And then I'm going to check if there's primes. I'm just thinking to myself, I'm using a for loop and I'm checking if it's prime. You may see me write English like this. Do not write English like this in your code. This is for your heart to understand this like semi-code math, because we'll have to turn this into something the computer can understand. Checking if it's prime is, I mean, it's not like we're not using large language models that can like turn that into something meaningful. We have to do that interpretation for the computer. Computer only knows for, while, so on and so forth. Okay. Okay, so write a program that finds all the primes up to 10,000. Okay, so that's my framework, right? It says create a list to store the primes. Oh, good, I already got that from the beginning. Which starts with just the number, with just the one prime number 2 in it. Okay, so I'm gonna say primes is a list, and the only things inside the list is the number 2. All right, that's what it says. Then for the numbers 3 to 10,000, okay, let's make a little adjustment here. Check whether the number is divisible by any of the primes in the list. How do I do that? Okay, so now let's think about this. So this will be inside of this thing, right? This is going to tell us. So let's go and we'll take this piece here, right? This is going to be, this black box is this line here, right? And we got to make sure we understand how this thing works. So user-defined function, what does it take in? The number we're checking, let's call it n. And all the primes we know about already. Good. And what do we want it to spit out? What? Your primes. You want it to give back the primes. So the question was, is this prime? Right? And what you want the computer to do is, if it's prime, do something. And if it's not prime, do something else. But what I want back is all the primes. Right? Okay. So spit out prime list. And I'm going to write that really small, but you know what I mean. Okay. So let's think about this not as a computer does it, but but let's do it as a human being. Okay. So first, sorry for folks online. Let's just move that over like that. Okay. So first, let's do n equals 2. Okay, that is the definition. We got that one already. And I'm checking n equals 3. So the first thing I'm going to do is which is what? 2. Okay, so 3 divided by 2. What is 3 divided by 2? We're just doing it as a human. 1.5. Okay, so this is not 0. So therefore, I know that. Well, which one? 50-50 chance. What? It's a prime. Good. So it is a prime. So I say prime. Okay, and then what do? I don't want factors. I never asked about factors. I've never once said factors. Well, hold on, hold on. I didn't do anything with this, right? So I got to do something with this information. You got to store it. Okay, so now I say, okay, it's prime. So I go and I back and I write 3. Good. Now I go n equals 4. Now what do? Check by 2. Okay, so 4 over 2 is 2, and it's 2. Oh, okay, so this is divisible. So this is not prime. Okay. Now, do I waste my time here and check 3? No. Come on, right? We have things to do. We got places to go. Talk about it again, right? So I'm gonna have to use a statement here, a clever statement. Something has got to cancel, right? Okay. So I'm gonna remember that. So I'm putting a little note to myself. Need something to leave the loop, right? That's a little note to future Mateo when he goes to code this up. So that's not prime. Do I store it? No, of course not. Good. Okay, so now the next one. N equals 5. I do. 5 divided by 2 is 0.5. Okay. So good. Is that prime? So far. But you are using information that is incorrect because you know that it's prime. But according to our computer, we don't know that it's prime yet. We haven't checked all of the primes, right? Okay, so what's the next one? 5 divided by 3. 5 divided by 3, right? And that is? I don't know. But you may know that it also has a remainder. Okay, so that's something else, right? 1 point something, 6, 7, right? Does that make sense? So now I checked both of them. And only when I got through the whole list was I allowed to say, oh, yes, this is 5. 5, our good old friendly prime. You see? So this is part of writing out that algorithm. You can see the process evolve. You go through each step. And then you take these steps and you put them into code. And you want to make sure that as you're looking at your paper, right, that has all these steps on it, that when you do the first couple, that they come out the right way. All right, that's how you know it went right. Okay. Does that make sense? So think about how you would make this definition here. And I'll tell you that it's a lot simpler than the one that we did in example 2.8. Does that make sense? Is anyone lost? Is anyone crying? Okay, just inside? Okay.